press the bell icon on the YouTube app and never miss another update.
So now let us take up specific heat capacity. Specific heat capacity. Okay. So now let me take up three different containers which are identical in their dimension. They are having same size, same shape, same weight. Okay, but they are made of different materials. I have a copper vessel. I have aluminum vessel. I have iron vessel. This is made of copper. This is aluminum. This is iron. So I am supplying same quantity of heat to these three containers during same interval of time. Okay, for 5 minutes I am supplying 100 joules of heat. 100 joules of heat. So when I supply 100 joules of heat for 5 minutes, you will find that the increase in temperature of these three containers are not same. Some containers quickly gets heated up compared to other two. For example, if you take a copper container, it quickly gets heated up compared to aluminum and iron. If you have a steel vessel, it also gets quickly heated up. So therefore, though you are supplying the same quantity of heat during the same interval of time, the rising temperature is not same in these three containers, because the nature of the container or nature of the material is different. It is the nature of the material which decides the rising temperature. Have you got my point? So one is made of copper, another one aluminum, another one iron. Since they differ in their constitution, right? The rising temperature is not same. So they are different. Okay, now I just take two copper containers. See, one is of this size, another one is big size. Right? I will supply same quantity of heat for same interval of time. You will find that the smaller container heats up quickly compared to the container having bigger dimension. So therefore, this tells you that the rising temperature also depend on the mass of the container. So therefore, the quantity of heat required to rise the temperature of a substance depends on mass of the container, depends on nature of the container, and also the difference in the temperature, the rise to which, or temperature difference, the extent to which the temperature got raised. See, therefore, if you take Q is the quantity of heat supplied to the material, and this is proportional to mass of the container and the rising temperature. Or Q is equal to, if I take the dQ is proportional to small quantity of heat is supplied. It's a small rise in temperature. Or dQ is equal to some constant. I take this constant as C. C into m, where C is called specific heat capacity and C is called specific heat capacity of the material. of the material. C is the specific heat capacity of the material. Then how we can define C? Suppose if M is equal to 1 and delta T becomes equal to 1 degree Celsius or 1 Kelvin. So in such a case, dQ becomes equal to C. Hence, specific heat capacity of a body is the amount of heat required to rise unit mass of the substance through unit rise in temperature. The quantity of heat required to rise the temperature of unit mass of the substance through unit degree Celsius or through unit Kelvin. See, it is a constant for the material and we call it as specific heat capacity. Have you got it? And it differs for different materials. Suppose we take aluminium. For aluminium it is about 900 joule per kg per Kelvin. Okay, this is the SI unit for specific heat capacity, joule per kg per Kelvin. So if you take copper, for copper it is 386.4 joule per kg per Kelvin. If you take water has a large value, 4186 joule per kg per Kelvin. To increase temperature of 1 kg of water through 1 degree Celsius, this much of heat is required. It's a very large value. Water is the liquid having a highest value for specific heat capacity, and mercury is the liquid which is having lowest value for specific heat capacity. But water is highest. See, that's why since water is having a very large value for specific heat capacity, it is used as a coolant in radiators of vehicles. In olden days, water was used as a coolant for buses and automobiles. The coolant is required, and water was used as a coolant for this because it has got very large value for specific heat capacity. Have you got it? So the air near sea or ocean is cooler because water has such a large value for specific heat capacity. When during a hot summer, if you go to seashore, see, you will never feel hotter, right? So there will be cold breeze blowing from surface of the sea towards the land. Okay. See, why that happens? Because water has very large value for specific heat capacity. Ground heats faster compared to water, right? Ground heats faster compared to water. Since water has a large value for specific heat capacity, it requires more heat to rise its temperature to very high value. See, that's the advantage of water. Okay. Since what is having such a high value, still we have ocean, lake, river, etc., etc. Otherwise, if it had a very low value, everything would have been gone by this time. Everything would have been dried out. See, that is the boon. See, that's why we take water as a universal solvent. It has so many unique features, See, that's why life is sustaining on Earth, in this planet, right? Okay. See, this is called specific heat capacity. The amount of heat required to rise the temperature of unit mass of the substance through unit degree Celsius or unit Kelvin is a constant for a given material, and we call it as specific heat capacity. So remember, during the change of state, if I write the equation for C is given by C is equal to dQ divided by M into delta T, M into delta T. Suppose there is a change of state, say ice is melting into water. See, when ice is melting into water, there is no change in temperature. Change in temperature is 0. In such a case, anything divided by 0 is infinity. Therefore, C will be infinity. Suppose if water is boiling got converted into steam, the change in temperature is 0. When water starts boiling at sea level, its temperature is 100 degrees Celsius. Steam is also having temperature 100 degrees Celsius, right? See, therefore, there is no change in temperature. See, therefore, during the change of state, the value for specific heat capacity is always infinity. This is a very important entrance question asked in the examination. What is the value for specific heat capacity during change of state? During change of state, delta T becomes equal to 0. And as a result, C tends to infinity. Right? Okay. Suppose if you take, instead of taking unit mass, if you are taking substance as a whole, if you take substance as a whole, a container as a whole, then we use the term called thermal capacity. Which therefore, what is thermal capacity? Thermal capacity of the body may be defined as the quantity of heat required to rise the given mass of the body through unit degree Celsius. The whole mass of the body through unit degree Celsius. How much heat is required, and that is what we call as heat capacity or thermal capacity. Heat capacity or thermal capacity. So it is indicated by S. S is equal to C by M. If you take the whole mass, see, therefore, this, there won't be any right. So you are taking the whole mass of the body, the amount of heat required. So will be larger. Amount of heat required will be larger. To increase the temperature of the whole container through unit degree Celsius, how much of heat is required? How much of heat is required? See, that is taken to be thermal capacity or heat capacity of the material. If you take unit mass, it is called specific heat capacity. If you take the whole mass, it is called thermal capacity. See, that's how they are related to each other. See, therefore, if you take S as the thermal capacity, it is equal to M times C. M times C. C is the specific heat capacity. When it is multiplied by M, so you are going to get for unit mass, specific heat capacity. For the whole mass, this is the. So when you come to gases, I told you earlier, we can study the gases, expansion of gases, either by keeping the volume constant or pressure constant. So therefore, here we make use of molar specific heat capacity. Molar specific heat capacity. Molar specific heat capacity is indicated by Cp, capital Cp, and Cv. What is Cp? Cp may be defined as amount of heat required to rise the temperature of 1 mole of gas through 1 Kelvin when pressure is kept constant. When you keep pressure as constant, the amount of heat required to rise the temperature of 1 mole of gas to 1 Kelvin, then we call it as Cp. What is Cv? The amount of heat required to rise the temperature of 1 mole of gas through 1 Kelvin when volume is kept constant, indicated by Cv. For example, see, we have a cylinder. This is fitted with a piston. Okay, movable piston. It can easily move, right? You just remember your cycle pump. Okay, it is a piston. There is a piston. See, here there is a gas, 1 mole of gas. Gas is there. So you are supplying heat to this gas. If I keep volume constant, see, I am not making this piston to move. The piston is fixed, right? It is not being allowed to move, right? It is tightly fixed. Now volume is kept constant. See, the whatever heat supplied by you increases only internal energy of the gas. There is only increase in internal energy. Piston cannot move, right? There is no external work done. There is only increase in internal energy of the gas. So volume is kept constant. This is CP. Now, let me take another situation where there is an allocation for movement of the piston. The piston is allowed to move. This is in some number supplying heat. When you supply heat, the amount of heat supplied not only increases the internal energy but also does some external work. The gas pushes the piston, therefore the piston moved at them over here. It pushes the piston upwards. You just remember your pressure cooker. When the steam pressure increases, then it pushes the weight which is kept on the lid of the cooker. It pushes the weight upwards. See, that is what we call it as external work done by the system. External work done by the steam in that case. Right here, external work done by the gas which is present inside. Therefore, when you keep pressure constant, there is not only increase in internal energy, it also does some external work. So for that reason, Cp is always greater than Cv. Cp is always greater than Cv. The amount of heat supplied not only increases the internal energy, but also does some work. See, therefore, more heat is required to rise the temperature through the same range as in case of volume is kept constant. See, therefore, for that reason, Cp is greater than Cv. And Cp and Cv are related by a equation which is given by Cp minus Cv is equal to R. That I will explain this in the third chapter, kinetic theory, how they are related, how we can get this equation. Cp minus Cv, or even in next chapter, thermodynamics also I can explain this. This is called Meyer's equation. See, therefore, difference between them is equal to universal gas constant. Okay. So, if you take helium gas, for helium, Cp value is around 20.4 joule per mole per Kelvin, and Cv will be around 12 point something, 12.2 or something joule per mole. See, it is different for different gases. See, their difference is equal to R. What is the value of R? 8.314 joule per mole per Kelvin. See, that is known to you. The value of R is a constant. So that constant for 1 mole of any gas. If you take 1 mole of any gas, 1 mole of any gas occupies same volume. See, that's why R is always constant. If you take 1 mole of any gas at standard temperature and pressure, it occupies the same volume. 22.4 cubic decimeter of volume. See, that's why the value of R remains constant, and hence it is called universal constant. So, on the basis of this, see, we have made gas thermometers because there is a constancy. Okay, you will get the accurate result. Have you got it? See, this is about specific heat capacity or molar specific heat capacity. So, therefore, for understanding the expansion of gases, you have to keep pressure constant or volume constant. Have you understood? So, therefore, this is a very, very important concept you have to remember. See, now we should consider one or two examples. Say before going to the next topic, let's consider one or two example. Specific heat of lead. Specific heat of lead. Specific heat of lead is 0.03 calorie per gram per degree Celsius. Instead of giving joule per kg per Kelvin, they are given in calorie per gram per degree Celsius. Find thermal capacity of thermal capacity of 500 gram of 500 gram of lead. So you know that thermal capacity is given by m times specific heat capacity. Okay. Here m is how much? 500 gram. M stands for mass 500, and C is 0.03. See, both are expressed in gram. See, that's why I am taking directly. See what you are going to get. So you are going to get 15 calorie per degree Celsius. See, in SI unit, if you want to express in SI unit, see, this will be 15 into 1 calorie is equal to 4.2 joules. 4.2 joules per Kelvin. Rise in temperature, degree Celsius is equal to degree Kelvin. Okay. If you take a rise in temperature, see, they are same. Okay. 63 joules per Kelvin. I got it. If 20 gram of water, 20 gram of water, 20 gram of water at 50 degrees Celsius, 50 degrees Celsius is mixed with 60 gram of water, 60 gram of water at 10 degrees Celsius, 10 degrees Celsius. Then final temperature of the mixture, then final temperature of the mixture. Say water at a different temperature, mix it together. Then they ask you to find out what is the final temperature. See, it is given by the relations theta mixture is equal to m1 s1 theta 1 plus m2 s2 theta 2 divided by m1 plus m2 m1 s1 plus m2. See, here both are water. Here S1 is equal to S2. Both are water. They are having same specific capacity. Or you can write C, no problem. C1, C2. Both are water. C1, C2 equal to C. See, therefore, you are going to get theta of mixture is equal to m1 theta 1 plus m2 theta 2 divided by m1 plus m2. Now you please put the values. One is 20 gram, which is at a temperature 50 degrees Celsius, plus 60 gram at a temperature 10 degrees Celsius, divided by 20 plus 60. So this will be 1600 divided by 80. So when you simplify this, so you are going to get temperature of the mixture as 20 degrees Celsius. In this way, see, there are so many simple problems that could be solved, see, related to specific heat capacity or heat capacity. We will consider such category when we go to entrance part. So, knowing of all this, we are in a position to understand calorimetry. Calorimetry. See, in my previous class, you come to know that the term calorie refers to heat. Okay. Actually, calorie was the unit used to in a CGS system. It was unit used to measure heat, used to express heat, calorie. So, therefore, calorimetry, calorie related to heat, metry, metron, measurement. See, calorimetry deals with the science of measurement of heat, how heat can be measured, what are the different techniques involved in the measurement of heat. All that comes under calorimetry. And to determine how much of heat is given or how much of heat is extracted from the system, how much of heat is given to the system or how much of heat is extracted from the system, we have different techniques, we have different experimental techniques, and we have a simple device which is used to measure how much of heat is absorbed or how much of heat is rejected. Correct. We call such device as calorimeter. It's a simple device. See, before going to the calorimeter, I must tell you what is the principle of calorimeter. Principle. Suppose if you consider any two substances which are at different temperature, we have two isolated systems which are maintaining at different temperatures, which are having different value for specific heat capacity. Okay, when they mixed with each other, the heat lost by the hot body is equal to heat gained by the cold body. We have two isolated systems which are maintaining at different temperatures or being mixed with each other. Heat lost by the hot body is always equal to heat gained by the cold body. See, that is the principle of calorimetry. In simple terms, amount of heat lost, amount of heat lost amount of heat equals amount of heat gained or I can write heat lost by hot body, heat lost by hot body is equal to heat gained by cold body. Heat lost by hot body is equal to heat gained by the cold body. This is the principle of calorimetry. Okay. And this calorimetry involves different methods. Okay. See, I can briefly tell you what are the basic methods involved in calorimetry. See, one is already as I mentioned, method of mixtures. Method of mixtures. Method of mixtures. When you mix bodies which are maintained, bodies having different thermal capacities or heat capacities which are maintained at different temperature. See, finally they will acquire a common temperature. Okay, and based on that you can calculate either how much heat is given or how much heat is gained or how much heat is lost, or you can determine specific heat capacity, or you can determine latent heat of fusion, right? Okay, all such constants could be determined experimentally. Okay, see, this is method of mixtures. And second one, method of cooling. This is also another popular method of cooling. Method of cooling. And we have method of change of state. Method of change of state. And we have electrical method, and even we have electrical method. So we will come across only this, even these two, these two are not there. So you will consider this in certain problems, but this is not included in your syllabus. Only second year you will understand certain basic things. Alright, method of mixtures, method of cooling, method of change of state, and also electrical. Now let me explain something about calorimeter. Calorimeter. See, calorimeter is a device which is based on the principle of calorimetry. See, this is a simple calorimeter. Okay, it is consisting of a lid. I will show this. So inside this, see, there is a copper vessel. Okay, there is a copper vessel, and there is a stirrer. See, this is used to stir the contents inside. Okay, it can be stirred like this. And we have a wooden box. Inside the wooden box there is a bad conductor. It may be a felt or it may be a wool. It is kept. It's an empty hollow wooden box, and we kept this so that, see, there will be it will be thermally insulated. See, there will be no chance of exchange of heat. See, whatever content we have taken, it is always taken inside this calorimeter. This is made of either copper or aluminum. See, I have taken copper calorimeter. Copper calorimeter is there. We will keep like this, and we will close this lid using we have a wooden lid which can be closed. If you want to measure the temperature, we have a thermometer which can be inserted like this. There is a hole provided, so we can insert like this. Now your calorimeter is ready. Calorimeter consisting of a wooden box, and inside the wooden box there is a felt or wool is present. It's a bad conductor, and we have a copper vessel along with a stirrer. Okay. Say, whatever content you want to take, you must take inside the copper vessel. And to note down the temperature, we have a thermometer. Okay. The entire thing is being completely covered, therefore there will be no chance of either conduction loss or convection loss or radiation loss. See, therefore you can gradually stir the liquid inside, okay, and study the variation of temperature. See, by this instrument, you can determine specific heat of a given solid. So either you can make use of two different liquids, mixing them, finding out final temperature. Either you can take a solid, heat the solid to certain temperature, and put the solid inside the water containing in calorimeter. Note down what is the temperature of the mixture. See, so let me take a sphere, a metal sphere. This metal sphere is kept inside boiling water. I take a vessel containing water, kept it on the stove, water started boiling. I keep a small sphere inside, iron sphere. After certain time, what is the temperature of the iron sphere? Iron sphere acquires the temperature of water. Now the temperature of iron sphere is 100 degrees Celsius. Now take out the iron sphere, quickly transfer to water taken inside this calorimeter. Then stir them inside this box, stir them. Heat lost by the sphere and heat gained by the water. Find out the final temperature of water. So using that final temperature, you can determine what is the specific heat capacity of the iron sphere. Say heat lost by the iron sphere is equal to heat gained by calorimeter and water. See, in this way, you can easily find out specific heat capacity of solids. And you can determine specific heat of a liquid. So you have to consider another liquid whose specific heat has to be determined. So along with this, right? By method of mixture also, we can determine specific heat capacity of liquid. Say the previous problem we have solved now. See, it is related to determining the specific heat capacity of a liquid. Final temperature of the mixture. Knowing the final temperature of the mixture, you can determine specific heat of second liquid. We have taken only water at different temperature. If you take water in one calorimeter and liquid in another calorimeter, when you know the initial temperature, mix them, find out the final temperature, and using them you can determine specific heat capacity of the liquid. See, that way, see, this is one of the easiest technique for determining so many constants related to heat. Okay. So therefore, in calorimetry we consider the measurement of heat, measurement of specific heat capacity, measurement of latent heat of fusion. Let us consider one simple problem which is related to this. See, in the lab there will be an experiment related to determining specific heat capacity, so that you will appreciate this. A sphere of aluminum, of mass 0.047 kg, placed for sufficient time in a vessel containing boiling water, so that temperature of sphere is 100 degrees Celsius. It is then transferred to immediately to 0.14 kg, copper calorimeter containing 0.25 kg of water at 20 degrees Celsius. If the temperature of water attains, a steady temperature, steady means constant, a steady temperature of 23 degrees Celsius. Calculate specific heat capacity of aluminum. Okay. See, this is our task. See, here we have a sphere of aluminum which is placed inside for a sufficient time inside a vessel containing water As I told you earlier, water started boiling. So that the sphere acquires the temperature of boiling water. So therefore now the sphere temperature is 100 degrees Celsius. So later on, so you have taken a calorimeter, copper calorimeter. What is the mass of the calorimeter? 0.14 kg. And this calorimeter contains 0.25 kg. 0.25 means 250 gram. 0.25 kg of water, 20 degrees Celsius. Water temperature is 20 degrees Celsius. 250 gram of water you have taken, its temperature is 20 degrees Celsius. Now the sphere temperature is 100 degrees Celsius. You have immediately you have transferred sphere inside the calorimeter and you start stirring. So that water acquires a steady temperature of 23 degree. Initially it was 20, now it became 23 degrees Celsius. They ask you to find out what is the specific capacity of oil. So therefore here there are two things. One is heat lost by the sphere, heat gained by the calorimeter plus heat gained by water. Both are to be taken into consideration. Therefore heat lost by aluminum sphere equals heat gained by calorimeter plus heat gained by water. Plus heat gained by water. Now heat lost by sphere. If this is given by mass of the sphere, specific capacity of aluminum, okay, and difference in temperature delta theta and delta T. Get. See here, mass of calorimeter. See, this is made of copper. Specific capacity of copper. This is mass of copper. Then rise in temperature. Plus mass of water, specific capacity of water, rise in temperature. So I take this delta T dash. Okay, rise is same for both of them. So now you just calculate this. See, this is mass of, this is 0.047. What is specific capacity of aluminum? You have to calculate this. Delta T is initial temperature 100 degree, final is 23 degree. What is mass of copper? Mass of copper is 0.14 kg. Specific capacity of copper usually given. Specific capacity of copper is 386.4 joule per kg per kg. So this is 386.4. What is delta T dash? Initial temperature was 20 degrees Celsius. Both water and calorimeter are at same temperature. Final temperature is 23. Therefore, difference is 23 minus 20. This is one thing. Plus mass of water 0.25. And you know that specific capacity of water is how much? Already known to you, 4186. 4186. And what is the difference in temperature? 23 minus 20. See, this is the case of water. Have you got my point? So you please simplify this. When you simplify this, you are going to get, say you multiply this, or you can take out 3 as common. You simplify this and find out what is the specific capacity of aluminum. So how much? It will be around 900, which is already known to you. Answer is known to you. It will be around 100. Sorry, 900. So you will get around 900. See, that's how so with the help of method of mixtures you can determine specific capacity. Well, now we shall move on to next important effect of heat, that is change of state. So we shall take up a change of state in the next session.